Hello, everyone. I think since they handed me the microphone, we're ready to go. Um, Next, we have someone coming from Expert Analytics, which is one of the places that I work. Felix, I've known Felix for on 8 or 9 years now. Right after I moved to Oslo. I don't know why I'm telling this story. But right after I moved to Oslo, a friend of mine that I knew from Germany said, "Hey, you should come to this housewarming party." So I showed up, and I was the first one there, and Felix happened to be the person who lived there, and he was like, "Who are you? Why are you at my house?" So, anyways, that's perhaps not a warm introduction to Felix. Felix has worked on a wide variety of problems, and now both laboratory, computational, and theoretical. So I think I'll stop talking now and let Felix get started. Thank you.
Thank you, John. Do you hear me? Yes. Yeah, okay. Yeah. Thanks a lot. Thanks a lot for the introduction. For me, it's like we met at the university. For me, it's actually the first time I gave a talk from the more the industrial applied part. In this workshop and also in some recent workshops and scenes I've visited here, I got the question, how is it in industry? Yeah, what's the difference? And then often the topic comes to whatever salary, work-life balance, and so on. But one big difference is also the people you work with and how they behave with you. So I just give you maybe for those who are from academia or mainly live in academia, some statements to think about that could be from I heard them in this way or another in the setting, in the industrial setting I was working with. So coming as let's say an IT professional, as a data scientist or a scientist to a company, I heard things like, for example, I do not believe in machine learning or in this AI tool. This is just a black box. So it's often are technical people, engineers, so they have some knowledge and they believe in their methods, but they are quite skeptic against like whatever AI is. Or another statement, we need to have a new AI initiative, otherwise we're left behind. So this is the fear, basically, that, yeah, maybe your competitor is now doing AI, and we have to do it also. So we need to put some money there and put some people together and make an AI hub, make an AI initiative to make this work, so that we are not the ones that fell behind. Yeah. Another statement is, I'm sure you can solve this in 3 days using AI. So there are sometimes like super high expectations to you as a, say, data scientist to solve a problem or to automate something that takes actually much longer than 3 days, let's say like that. Yeah. Another one is, I do not want to be replaced by some AI. You often come to a situation that you automate processes. You probably don't automate people, but you automate tasks that people do. And of course, at one point, you might just need 2 of these people doing what you had 5 people employed before. So I think all these statements, they have a truth behind it. There's a truth behind all the statements, and you have to see, like, you can't look from that above perspective anymore. If this is your coworker you're working directly with, yeah. If this is the person you talk to daily, yeah, you have to level out these fears and expectations. So this is like one perspective for me, like one new thing I learned coming from academia to industrial setting. But let's talk about another thing. Let's talk about the issues related to A chalk-based reservoir. This is from, you can guess, from a customer story based in the oil and gas sector. So you know this story. So dinosaurs die, and there are some prehistoric trees, and then this is covered by stone mud, and this will be digged in the ground, and at one point this becomes liquid and it becomes oil, and then you can drill a hole down there and make a lot of money, buy a helicopter, buy a sailing ship or so. So yeah, that's the really short story. The special thing about this one here is this reservoir here, which is often sandstone, is in this case is chalk. It is kind of unique. It's kind of a unicorn in the field. It's not like a lot of oil reservoirs are chalk. This is very special. And compared to sandstone, chalk is less permeable. Chalk is much weaker, and it consists of much finer grains. Here you can see a SEM image of such chalks, like actually from a reservoir, which you see these coccolid structures. I showed before, like when this coccolid is like 20 micron, more or less sized algae chalk elements, which are more like affected by corrosion or by overgrowth. This is how it looks like, the chalk in this reservoir. So there are several issues related to this chalk reservoir. And the main issue that there are failures like tensional and shear failure due to too high drawdown. The drawdown is usually like how much you suck on that reservoir, let's say like that. The pressure gradient to the next sensor, and the migrating fines, and there's also at one point you put pump water at another point of the reservoir and you get it out. So this chalk, if it fails, it can lead something which is called chalk liquefaction. So this chalk can really look like toothpaste. If you add some water or apply some pressure, it becomes smooth, and the entire structure fails. And here you see example of measurements of water weakening, actually, of chalk. So this can lead to plugging of pores in the formation, and this chalk, these fines, they can accumulate in the liners in the wells, and this might need to lead to a reduction or partial loss of the production. You need probably even to stop and to make some really expensive clean-outs of these wells, or even such a well can, what they say, die. You can't produce it anymore. And this is all really, really expensive. So they spent some money and some research on it. And the first thing, what do you do if you have an issue? You call the chalk busters. So unfortunately, they were a little bit less creative and called that not the chalk busters, but the advanced chalk influx advisor team. So this project is about giving what kind of tools can we make to help a more informed, to help the engineers driving these wells to have a more informed decision on how to operate it and to avoid such severe influxes. This team consists of experts of different fields coming from rock mechanics, reservoir modeling, petroleum engineering, geochemistry, production chemistry, metering, data science. And the objectives of this project is having experimental studies on chalk to how this thing works, to get more knowledge, increase the knowledge base, having lab tests and modeling. Field tests of instrumentation, mainly to measure chalk, and models to assist the asset, what's the people managing this field. When it comes to chalk transport, so there's a lack of knowledge about where and under which conditions the chalk sediment accumulates in the well, in the liners. Yeah? So flow rates that are too high can lead to destabilization and failure of the reservoir rock. So this is this drawdown. You don't want to make this too high, then it can lead to failures. And flow rates that are too low, then we can imagine that everything which is in the well deposits, and it might lead to plugging. So it's you need to kind of be in this sweet spot, and there's some knowledge needed. So how is chalk transport in general? What are sedimentation and critical velocity to sedimentation, drainment? What are the relevant effects to consider in this entire thing? What are critical parameters? And what have these things affect on the sensor? And all this is going on. If you're not familiar with multi-phase flow, you can imagine like it's not just one-phase fluid or something through a pipe, but there are many possible phases for two phases now. Let's say this is oil and gas. There are different kinds of phases. Could be dispersed bubble flow or underflow. Often I have an entire other project dealing with slug flow, which causes a lot of issues in this thing. So it's getting, and this is just for vertical flow in a certain scenario. It gets much more complicated if you add different angles. It could be about variety in this what's called GRA, the gas to oil ratio, and of course, since there is basically no gas when the pressure is super high, when it's down in the reservoir, and then when it comes up, there's a lot of gas. So everything is in a transient thing. It's never like an equilibrium state. So everything is like, this is like equilibrium phase diagram. It's never been there. It's just somewhere. So it's quite complicated, and it's got even more complicated if you add water. And meanwhile, all wells in this field produce water as well. And on the other hand, there is also a lackage of a good chalk detection system to monitor the background chalk concentration and give hints on healthiness of the well. Of course, it's important to detect the chalk to know what's going on there. There are different methods, theoretically, to detect chalk. Like the most important, the simplest one, is mainly what is on the upper left. This is just a microphone, basically. It's called acoustic sand detector. It's a microphone you place somewhere behind the band, and then you detect the hitting of the particles on that. This instrument, it's very important because this is installed in the field, but it's not optimized for chalk, and it's not, well, there is a signal, but it's not, you can't really measure, say you measure chalk so far. It's not working as that. But it could be an interesting instrument. Other instrument is like this flow meter, which works with gamma absorption. You can use cameras, just take a small diluted sample out of that and observe it optically. This instrument here works with X-ray fluorescence, and we also had a project with distributed fiber optics along some test wells. So these are theoretically instruments that there is a perspective of them to measure chalk, but there's a lot of things that need to be proven first, and there are some methods that are really sensitive, but it's really hard to implement in the field to get some sample in there. So there is a lack of knowledge on how to deal with these methods and how sensitive they are, and also how to apply it in the field. Like having all these questions which basically, if we can't answer these questions, we can give better guidelines how to optimize the production parameters in the field and how identify precursors of like these severe simulations. So that's where I suggested to make some experimental, like this is a slide I actually try to push for making some experiments there, or to motivate that. And some experiments we did last year at SINTEF, in the multi-phase laboratory in Tiller, close to Trondheim. So they have huge instrumentation to make flow loops. Like this mid-sized flow loop, it's mid-sized because it's like a 2-inch pipe. They have also like 1-to-1 real-sized these instruments outside 1 kilometer, impressive instrumentation. But we did mainly experiments here in a what's called a medium-sized flow loop, and detect like measured chalk. I think have to measure chalk sedimentation velocities and entrainment velocity depending on the angle, depending on the water cut and GOR, so the ratio between oil, water, gas. Wetting of the chalk, if it's been water wetted or oil wetted. And we also examined effects like agglomeration and emulsification in this instrument. And some other experiments were more like benchtop, like here, this on the lower right. You take some oil, water mixtures, and you add a certain amount of chalk, and you shake, and you see, like, depending on the chalk concentration, the more chalk you add, there's more emulsification in that. So chalk also acts as an emulsifier. This calls this like this so-called Pickering emulsions. You can imagine, like, you can maybe see it here on the upper right. This is a micrograph of such chalk, oil, water mixture. And you see that the chalk basically tends to be at the interface of oil and water. So that's why it basically stabilizes these small bubbles or so. Yeah. Chalk has also a shear thinning effect. The sedimentation depends on wetting. And one other thing is that the chemistry, like it's called Exol. It's just like a oil you can buy in bottles in the supermarket, more or less. That the real crude has chemically much more diverse. So it has like ingredients that are what they call waxes. The waxes are they have a very low point of solidation, yeah. And also a lot of ingredients that affect the surface chemistry. Yeah. But let's come more to the data part. So what are the models we basically try, or like what are the information we try to get out of this all these experiments, and also what other models we try to implement to help basically the field to operate better. One slide about the data that's available. There is data, basically, it's quite limited. So the data we have is a pressure sensor and a temperature sensor downhole here, the reservoir, and a pressure and temperature sensor at the what's called wellhead up there. And then there is this ASD, this acoustic sand detector, this microphone behind the band. And there are also these two operating parameters. They're basically used to operate a well. One is the choke. It's a valve, the main valve to control the flow. And the other one is one of, or the most prominent artificial lift method, what I call it, what it's called. So you pump some gas down in the well. This is the annulus, and this is the actual well. and this gas enters the actual well, and then this entire like column of liquid gets lighter and it's lifted up. Yeah. So that's the gas lift. These are the operational parameters. Some words about the data quality and the characteristics. So these are very long time series, often more than 20 years. But the data quality is varying a lot and is, let's say, challenging often. And also the environmental boundary conditions of the system change with time. So, for example, the reservoir pressure is decaying with time. So you can't really compare, or the water content, or so you can't really compare the well 10 years ago with the same well now. Well, you can compare, but it's difficult. And it's also very difficult to compare the wells between each other because everything is different. They are constructed different. They have totally different geometry and might differ from a lot of perspectives. One model implemented is the so-called event detector. So what's an event? Event, you see these small abrupt changes here in these pressure sensors. So that's when somewhere in the system some blockage appears or is released, like it's what they call a pop or blockage. And this can happen in different sections, either in the so-called IPR section, like before the bottom hole, in the vertical line here, VLP, or in like after this wellhead. And this is more like how you can imagine. This is a huge pop, I think, where how this looks like in detail. Of course, this is kind of a huge one, and some are much minor. And this event detector just uses these rules like this pressure goes up and this pressure goes down, and then it must be whatever pop in these sections. And then also ruling out, well, we actually didn't change anything. We didn't close the valve at the same time. Then you expect something different. So that detects the events, and then here you can see the result that here, these are the detected events in this period of time. I mentioned it because that's something, it's one indicator for the healthiness of the well. So this is one model that's implemented so far. Another model is about reservoir weakening or maximal drawdown. That's a rock mechanic model, basically. How large can this drawdown be before this rock fails, before the chalk fails? Transport model, like you can, by knowing some velocities or pressures here, people know how to calculate the flow in the entire system, and then you can say, yeah, well, this velocity is actually enough to transport the chalk or not. One model is to improve the specificity to chalk in the acoustic sand detector to make this, like it's made for sand, to make it more like filter out maybe fluid noises and other stuff to make it more feasible for chalk. And also one model is to detect gradual blockages by comparing, like basically, yeah, with this valve opening and this pressure, I should have this flow, but it's actually less, kind of, yeah. So that's a way to detect the gradual blockage. And now there comes more, this is what has been so far, and the development which is going on now is to go more from this analysis thing to a prediction, to develop models that can evaluate the risk of the influxes to allow the people to actually react on this. So this is more the actual machine learning part. So we heard in the recent talk that we can't predict earthquakes. But you see these maps of earthquakes from the last century. And you see they accumulate at certain places, and from that you can, of course, derive a risk map of, depending on where you are, how high is the risk. to that you experience an earthquake. So similar, we can probably not predict individual events, but we can have a good chance to evaluate the risk or the probability of events happening or of severe influxes and indicate if that the healthiness of a well and to avoid this influxes. That's, by the way, like what I mentioned in the beginning, to level out the expectations. That's a slide I used to motivate that. As other models I will quickly talk about. The first one is actually not a model, it's just a statistical feature database. So feature extraction is something everybody does. Why do I mention that? I think there's more than a standard deviation and a mean in a certain time series slot, let's say. One thing is that well, we use this feature database, of course, for future it should be used for machine learning, but it's also used to do statistics on that. And it's also kind of a product that we deliver. So not just I or we as the people doing more data science in this group should be able to do that, but everybody say, like, if you hint out like this is an interesting feature, look at it, and everybody should have access to it and look at it and extract the data and do their own statistics. This is one example of that. It's center of mass of wellhead pressure, bottom hole pressure, and one interesting point I added here is the time to the next event. So it's here categorized between time to next event in below 1 day, 1 day to a week, more than a week. And you see like what's accumulated here, or in this graph here, this is like at the low center of mass, mainly of the wellhead pressure. It's really close to event. So this might be a precursor to events, and people can look at that. Yeah, what I just said. Then one can, of course, do this a bit more systematically and use a classification model to look at what features are actually relevant, and or use like all features together to evaluate, is this actually like before an event or far from it, is this a good or a bad situation? And well, the result of that is here in red. It's the prediction, and in blue it's what's actually the times and point that actually have been before an event. Plotted as the wellhead pressure, you see that they correlate. Of course, not perfectly, but there is a quite good correlation in most of the cases I tested so far. This is just a confusion matrix. I think it's actually better than this confusion matrix says, because of course if you say it's kind of unrealistic that this classification says, yeah, well now it's 25 hours before an event and now it's 23 hours, and it just switches from 0 to 1, so to say. And here's the temporal correlation of the prediction and the number of labeled hours per day as being before an event. Another model is a quantile regression model, basically predicting one of these variables that we are having available. For example, here, the wellhead pressure based on the others, saying, training the model with that, and then comparing the actual result with this prediction. That's how it looks like. Here's a training period in blue, and then in red is the prediction based on these other pyramids. The reality looks like that. So these high spikes are because they closed some valves or so, and it even gets this quite good actually, but they tend to differ for longer time scales. And this might be a hint, for example, that the reservoir pressure decreases. Actually, is something changing, or that there's some a gradual blockage in the system or so. The difficulty here is how to basically interpret, so like how to drain and what to interpret. You don't want just the perfect prediction of the wellhead pressure. You have that, but like depending on what you drain it, what's the actual readout if this differs from that? Yeah, and that's one of the ideas that could be used to depends on the training, but to basically see something that's on the longer scale, maybe it differs, and then find reasons why. If this could be better evaluated. Then I use matrix profiling, an algorithm, a library, Stumpy, and I really like the way that how they describe Stumpy in the web page. What it is, so Stumpy is a Python library that computes something called the matrix profile, which is just an academic way of saying for every green subsequence in your time series, it automatically identifies the corresponding nearest neighbor in gray. And then you get something like this. So there's a metric, and then you have something like this matrix profile saying, yeah, there's something which is I find something that looks really similar, or that's nothing that's really similar. And there are different ideas to apply this method to identify events. Like here, it's used for different sensors, bottom hole pressure, bottom hole temperature, wellhead pressure. Find something, basically telling the algorithm, find something which is similar to this red part snippet, what they call motif. Which is blockage, I think. And then it finds this green part, which looks really similar, and you can say, yeah, well, that's probably the same physics behind that. If the sensors look that similar, it might be actually the same thing happening at this point as well. You can, with the same idea, you can also try to identify precursors of event. So basically, it's telling like, now soon is something happening. Detect outliers or unexpected behavior, because this should look actually really different to what we've seen before. I try to do a segmentation to detect different regimes or situation. So here the concept is to compare. You don't just get the distance to the nearest neighbor, but you get also the index to the next neighbor. And if there is a segment where every next neighbor is kind of more or less in this, and there's not that many neighbors in the next segment, then it might be, okay, that's probably something which does just look different than this one. Yeah. So that's the idea here. To define, like, that's probably now a different situation in the well, and we have to look into that. Something has changed. And the last and the most important point probably here is the health index, because that's like first that probably goes into production. That's another topic, that like bringing something into production in an industrial setting is much more difficult than in an academic setting. We often like stop at the point where you say, yeah, that's a proof of concept. It works now. And then that's often where you basically start and have to prove that it works like 100%. And yeah, so that's called the health index. And here the idea is just testing the similarity between certain periods in time that were considered as bad and to certain periods of time where it's considered as good. Yeah, where like nothing, every well was fine, or there were a lot of things happening and we always lost it, kind of, or a lot of events. These are these two distances here on the top. On the bottom, you see now this health index indicating, or kind of nicely predicting, yeah, well, now it's not so good, and then it also correlates quite well with a lot of events are happening, a lot of things are happening in this well during this time. that's the same idea applied to now actual failures of a well. So, but there we have really bad statistics, like as we heard in some talks before. Yeah, there were some failures, but there are small numbers, so we can't really have a good statistics on that. But trying that, finding a measure to between this is long before a failure or short before a failure, and see this, also this index decays like, this is another time scale. Now this is more like months, several months before the next failure, this index already really decayed and indicated maybe, yeah, there's something that it doesn't look so healthy anymore. Yeah. Yeah, and all these methods that should finally guide into one health index and help to indicate the well behavior. And so this should be a multimodal approach to evaluate the healthiness of a well and to warn for specific hazards. Yeah, that's about it from my side. I hope you're convinced that the chalkbox busters can solve this issue. Thanks.
So, are there questions for Felix? So one question that I have is if you could talk more about the Stumpy model, because I think that I think for some of the seismology-focused people in the room, that might it's very similar to like a matched filter, but it's like that on steroids, from my understanding.
Yes. What's your question?
Yeah, that's not really a question, is it? It's because I guess just like describe more about how it works.
Yeah, it works as that like they basically find a metric between, like, you take a certain snippet, they call a motif, like a time segment of a defined size or defined length, and then you find in the entire, either in this time series or in another time series, something which looks similar, defining a metric. Like, there are different metrics that actually are implemented in that. And then this algorithm takes the smallest distance of all this, and this is the matrix profile. So the idea is, okay, I found something which looks really, really similar, yeah, and here's the index to that. You can do this in principle brute force, but this algorithm makes it in an efficient way that you can actually use it. Because if you do the numbers, if you do the calculation, if you do brute force, it's basically impossible for, like, pretty soon, yeah. At least if you don't use whatever kind of computing powers. Yeah. That's the idea behind it. Then it's just pattern matching. Yeah, you have this pattern that looks really. This pattern looks similar to that one. I like this algorithm very much because it's, yeah, you can so easily imagine it. Yeah, so this looks similar than this one. That fits in my brain. That I can make a model out of that. Yeah.
Are there more questions for Felix? No. No. Well, then I think we should move to our next speaker, because I didn't realize this at the last time, but we're kind of behind schedule, so that was pointed out to me. So let's thank Felix again.